Well, good morning, dear. Welcome back. Today we are going to uh, tell you the story of logistic regression. In machine learning, in my opinion, logistic regression as a classifier, as a binary classifier, and support vector machine, these two tool or the model, perhaps the most sophisticated model based on simple, intuitive, but deep thinking or sophisticated thinking compared to, say, other classifier like decision tree, random forest, KNN. Those are relatively based on pretty simple concept. They are also used in industry very much, but idea are more sophisticated in logistic regression and support vector machine. So we are fortunate today we'll study logistic regression as a binary classifier. In my earlier class, what I did, I tried to tell you that that why that support vector, why that linear regression model is not capable of classifying the samples. Okay, I hope you understood the concept. So then what we did, we introduced a sophisticated concept that predictor will be equals to a predictor will be a function of W transpose X, and this function is a logistic function. So the definition of predictor in case of logistic regression is 1 by 1 plus e to the power minus W transpose X. Actually, why this concept came, right? This we were looking for a function which has two asymptotes. Okay, because while we were trying to use linear regression model for classification, the basic problem was these samples were getting mixed up depending on the regression line. Okay, so that here such thing will not happen. See, these samples and these samples, they are the two class, binary class, right? This sample belongs to class 1 and these samples belong to class 2. That what this function is doing, logistic function or S function, so it looks like S, that's why sometimes it is also called S function, they are the same. They are actually separating the samples towards the asymptote. Okay, and if now you calculate this predictor, what it is actually calculating, explicitly it is calculating the probability of a given sample to belong to a particular class, isn't it? Say for example, you have design W transpose X equals to W0 X0 plus W1 X1 plus W2 X2, right? So this is your say predictor, that is W0 plus W1 X1 plus W2 X2, right? So this is actually W transpose X equals to this. Okay, so e to the power minus W transpose X 1 by 1 plus e to the power minus W transpose X you can calculate, provided you know these parameters, right? Wait a minute, I have not discussed anything about how to get these parameters, but suppose that we will discuss, and that's the most interesting part of logistic regression. Suppose you know this parameter somehow, okay, and suppose you have some values like w0 equal to -5, w1 equal to 2, So what the predictor is actually calculating, if you put these values for any sample, this is known, right? This entire thing is known provided these are known, and you have these given samples. Okay, so this is a quantity now, and put it here 1 by 1 plus e to the power something. This will be a function. This will be a value between 0 and 1. Okay, so what you will get if the sample is here, for example, you will get some values. Okay, maybe 0.6. Okay, so this is say is an example, right? 0.6. So in that case, what is this? The probability that sample belongs to class 1 is 0.6. Okay, likewise. Okay, all these things actually, this is very interesting thing to note, that your this predictor is actually calculating for a given sample what is the probability it belongs to a class. Is it clear? Okay. Now implicitly it is also calculating the decision boundary. Let us see how. Okay. So if I just draw this again, this is my sigmoid function. Okay. So this is w transpose x. So you have already seen, if it is my z, and this is the definition of this function, sigmoid function, right? So sigmoid function will actually, if it is 0, 1 and in between say 0.5, so it will give you the asymptotes passing through 0.5. Okay. Okay. So this z is here actually the substitute w transpose x. W transpose x, w is the parameter. So if z greater than 0, that means w transpose t greater than 0, then what? That means it is threshold is 0.5. 0, if it had been 0, then it would have been 0.5, but it's greater than 0. That means it belongs to a class 1. If w transpose x less than 0, then it belongs to a, so w transpose x greater than equal to 0, the sample belongs to class y equal to 1. So I have two classes, right? Y equal to 0, class y equal to 1. And then if w transpose t, the w transpose x less than 0, the sample belongs to class y equal to 0. It's very simple, no confusion. This is I am telling implicitly, because you see my predictor is this function, okay, and within this function you have this e to the power minus w transpose x, and this is actually condition. If this is greater than equal to 0, then it belongs to, by virtue of the sigmoid function, characteristic of the sigmoid function, which is passing through the threshold 0.5. Okay, by virtue of that, if w transpose x greater than 0, means in this zone everything belongs to class 1. If it is in this zone, everything belongs to this. Okay. So this is beautiful observation. So implicitly means within that function itself, you are able to get now the decision boundary. Now suppose pictorially I am showing you I have two class. Okay. So this is belong to a y equal to 1 class. This is belong to y equal to 0 class. Okay. So say this is y equal to 0 class, then suppose now W transpose T is your this is the predictor. Okay, I am designing it, and suppose whimsically I have not yet talked, as I told, that how to get this parameter, but somehow suppose the parameter is known, then you are getting this. So this is the equation of this line, right? So this is the equation of the line, which is, so this is called the decision boundary. Here the sample lies here, then it belongs to y equal to 1 class, sample belongs here. So this actually implicitly the predictor is designing the decision boundary. Is it clear? It has to be clearly understood. It's very simple concept, but need to observe from the function itself, and I explained already. Okay. Now suppose is it that only it could be decision boundary could be a straight line? Not necessarily. Logistic regression can also design a boundary, decision boundary, which is nonlinear in nature. For example, these are my nonlinear samples. Okay, this is positive sample, say y equal to 1, negative sample y equal to 0. So I can design, again how you are designing, that is different issue, but I can design, if you can, I can design a predictor of this shape, seeing that okay, it seems that this is a nonlinear, there exists a nonlinear decision boundary, and then we will discuss another story how to get this parameter. Suppose the parameter is like this, then if you design this W transpose X like this, then you will be able to get a decision boundary which is circle. Okay, so beyond this, all samples are belongs to y equal to 1 here. Okay, so if it is put the samples now, if it is here, then is it clear now? I think it is clear. If not, let us know. Similarly, I can just design more complicated my predictor. Okay, so in case of linear regression, G was not there. Only here, G is a logistic function which is just separating forcibly the samples. Okay, so the decision boundary could be also like this. So this is kind of decision boundary you are getting implicitly from here, from this predictor, and explicitly just you take the predictor, put all these values, you will get a probability. For any sample, you get a probability belonging to a class y equal to 1. Okay, provided I am designing W properly. So far so good, right? Now the main issue, focus your attention here please, because this is the most interesting story. How to design a cost function where I can run gradient descent algorithm and get the parameters, because so far you have seen that parameters, how I am getting these W, W1, W2, W3, we have not talked anything, right? For this, for getting these parameters, what you need? You need a same old story. Okay, you need a cost function, and in the process of minimizing the cost, your parameter will be evolved. Okay, so let us see how to design cost function for logistic regression. First of all, this is the cost function for linear regression. Okay, when this is W transpose X. Okay, Hx parameterized by W. If it is W transpose X, then this is the linear regression model we have seen. Okay, and very good, because in that case the linear regression model we had a good function. This is called convex function. Okay, and this function was qualified enough to give us the parameters by running gradient descent algorithm. Now let us see, I forcibly just for logistic regression, this is a logistic function, right? This is a logistic function. Predictor is my logistic function, and the nature of this is like this. Okay. So if I blindly put this function here, minus y squared, and then formulate my cost function, then what will happen? The convexity of the function will be lost. It will be a good exercise if you do it. Okay. Convexity, that means something like this it will be. What is the characteristic of this function, cost function? You have local optima here, local minima here, 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 here. So anywhere, if you are now running gradient descent algorithm starting either from this direction or this direction, there is every possibility that your algorithm will stuck here. Means here the algorithm will tell that I have got a W optimum value, and you will stop, but you have not actually reached the optimum value. Okay. So that is called the iteration is trapped in the local minima here, and that's disastrous, because with this W, if you design your predictor, then it will misclassify. Okay. So that is not acceptable, not acceptable. Okay. So we cannot simply put the predictor as a sigmoid function and derive our cost function. Okay. So what to do? We are taking a digression and just recap a little bit information theory, Shannon's information theory. This is I, according to Shannon, I, which is information, is equals to minus log of probability of x, where probability lies between 0 and 1. X is any stochastic event. Okay. And you know, since it is a fraction lying between 0 and 1, we have added a minus sign, because log of that log of the function will be always negative. So it is inconvenient. So negative already is there, and then this itself is negative, will be always positive. Information will be positive. So information can be calculated like this. Okay. And based on that, so and what we are trying to do in machine learning, we are trying to extract the information hidden in the data. So this is the definition of information, and also we know that average information is, according to Shannon's theory, is called entropy. So entropy is actually H denoted by H, which is nothing but minus average of Px log Px. Okay. So this is the very important concept. This entropy is different than your thermodynamics entropy. Conceptually there are similarities, but entirely they are different. We can talk about that. But here, see, this is the behavior of, if I just make a plot now, okay, entropy versus probability. Okay, just you can plot and you will see that if the probability of x, which is a stochastic event, is 0, then there is no entropy. Okay, entropy is 0, that means there is no information, useful information. Okay. So when it is increasing, entropy is increasing. Entropy increasing means there are uncertainty in the data. That means information is there, and that is our interest. Okay. And the entropy becomes maximum, which is equals to 1, when probability of x, which is a stochastic, occur in x, which is a stochastic event, is 0.5. Then again it decreases. Now we would like to use this beautiful function for our classification problem. Okay. Now say I have a sample which I know probability of occurring is here. Okay. So entropy will be less. So I want to, or here then entropy will be again less, because there are certainty. Certainty means it is towards. So if this is my, just virtually you can imagine, this is my class level 0, this is 1, then I have 2 class. So more towards this, entropy is small, that means there is no uncertainty. Certainly that sample belongs to 0 class, y equal to 0 class, and here also certainly it belongs to y equal to 1 class. So maximum interesting thing is here, okay. So I have 0.5 entropy is maximum, okay. What does it mean? It means, okay, so it means that I need to draw a decision boundary for classification, right? Say I have 2 classes. I would like to draw a decision boundary like this, okay. So this actually corresponds to 0.5 in my logistic function. You remember that 0.5, okay, because that is the most uncertain. When a sample is here, is the most uncertain. You do not know whether it will just belong, to class 1 or it belongs to class 0. So this is the most uncertainty, right? And there, if I critical, this is a critical point. Here, if I can make my decision boundary, then I got it, because this is the most critical one. More than that is actually belonging to y equal to 1 class. Less than this belongs to y equal to 0 class, okay. So this is very interesting. We would like to exploit that, okay. So I would like to design parameter, okay, which will give me explicitly these parameters I would like to design now, okay. So Shannon's information, exploiting Shannon's information theory, we are convinced that 0.5 probability is very important thing for our decision boundary, and can we exploit that in getting a function which will look like, because this function is very great. Now if we want, this is again a convex function, right? Can we get this type of function exploiting Shannon's information theory, okay? That will be our basic objective, which I think I will spend another class, because this is the most important and very intuitive, very close to everybody's heart who understand this, okay. Till then, bless you all. Today is Teachers' Day, and stay safe, and goodbye.